Okay.
Right, so the talk in afternoon is given by Sukjoo Lee from IPS, and the title is about symplectic leaves of meromorphic Higgs bosons. Yeah, please.
Okay. Yeah. Thank you for the invitation. It's a great pleasure to be here. It's my first time at IPMU. It's amazing. I haven't explored that much, but hope I can after this talk. So this is all going to work with Hitchin Lee. Then I'm going to present some our series of works. And then one of the motivation is to revisit symplectic leaves of the meromorphic Higgs boson. So let me get into that first. So first slide is about basically just setting up the notation. Everyone in this room may know all of this. So for me, this is C is a smooth projective curve. I work over the complex number, and then the G go by genus. And I say a letter R and D for the rank and degree. And for simplicity, I assume that they're co-prime. It's not necessary, but it's easier. And then notation for Higgs bundle is the E, which is a rank R and degree D bundle by Higgs field. So let's first consider the Kc valued Higgs bundle. And I denote H to be the moduli space of stable, semi-stable, because the rank and degree co-prime of solution. And then we have Hitchin map, coefficients of the characteristic part and characteristic polynomial. And the key properties I want to study or motivate it is that the meromorphic symplectic, this is everyone knows, that there's symplectic structures, and also it forms called algebraic integrable system. It's a Lagrangian fibration. The generic fiber is an abelian variety, particularly Jacobian of the smooth spectral curve. And then one of the property also we have is that the dimension of the source is twice of the dimension of the base. And also we often consider this as an affine space. So this is all classical result. So I'm going to think about the variance of this Higgs bundle story by allowing the data of the poles. So I allow the Higgs field as a pole, which means that I choose some collection of the points and then twisted by this D. Okay. But I use the same notation because this is our main object. So consider the moduli space of a stable KCD valued Higgs bundle, we often call meromorphic Higgs bundle. So we have Hitchin map, the basis should be changed. And throughout the talks, I only consider that the case where these 1 point. Okay, just for simplicity. But when G equals 0, then at least you allow more than 3 points. But that's technical part. So the similar key properties I want to revisit is that the independent work of Hitchin and Martin, so almost 30 years ago, if H is no longer symplectic but it's Poisson. And then the Hitchin morphism is an algebraic Poisson integral system. It's not Lagrangian anymore. The dimension of the source is less than dimension of the twice of the base. But still, we have a genetic fiber is an abelian variety. This is a well-known structure already 30 years ago. But there are still remaining questions. To understand this Poisson geometry or Poisson variety is one of the key things is that understand how it is foliated. So my first question is, what are the symplectic leaves? Which means that maximal connected symplectic sum manifold. whose characteristic distribution, so whose tangent space is a characteristic distribution. Let's call it integral. So in this case, we know the candidates. The candidates is actually the locus where the residue lies in certain adjoint orbits. So here, one remark is that I don't consider, I don't only consider the nilpotent orbit. This should be like any orbits, any adjoint orbit. So I put the candidate here. So in order to prove that this is actually symplectic leaf, I need to show that locally, using the deformation theory, prove that this is smooth, and then tangent space is the characteristic distribution, and so on. And globally, we need to prove that this moduli space is connected. So in this talk, I'm not going to focus on the infinitesimal story because this is quite well known. In some sense, it's quite expected. But the global geometry is, as far as I know, is still missing. So once we know what the symplectic leaves are, the natural question is, okay, let's restrict our Hitchin morphism to this locus. Okay, and because this is symplectic, I want to be this have some like integrable system structure. That means I need to describe like a base. The base should be like smaller than that because it has to satisfy this definition. And I also want this to be the the second, I want to understand fiber, genetic fiber. Okay. I need to prove that this is a abelian variety. This is the second question. And then one other related question is that, in fact, it's much easier, in some sense, like deal with the closure of this orbit. Because this moduli space is locally closed, it's quite subtle to play with. So it's natural to think about this closure and then the moduli space. I denote H O bar, whose locus lies in the closure of this orbit. Then the general fact is that this is singular. So one reason is that this guy is singular. And globally, the first question is whether this locus is actually the closure of our Higgs O. This is quite a natural question, but without knowing some connectedness, we cannot say anything about this. So a more interesting question is that what kind of singularities it has. So classical, like a Springer theory, then we know that we have like a symplectic resolutions of this kind. So it is natural to expect that we also have the symplectic resolution of this. So these are like the three main questions I'm going to talk about. And our goal is to answer to these questions, but using the parabolic Higgs bundle. Okay, I first solve very similar questions to the parabolic Higgs bundle, and then use that like to answer these three questions. That's the plot of the talk. Any questions? Okay. So let me move on. So to define the parabolic Higgs bundle, I need to fix or choose a one combinatorial data, which is partition of our rank. And I denote like underlying M. And then parabolic Higgs bundle is a triple where this E and phi forms a meromorphic Higgs bundle. And I could put the parabolic structure at each point like a P. So earlier I assumed that like a 1 point case divisor is 1 point case, which I denote P. But it's not like arbitrary filtration. It has to like talk to this combinatorial data in the sense that associated pieces as a dimension prescribed by this combinatorial data partition. And then also it's compatible with the residue. So this is a definition of the parabolic Higgs bundle. And to define moduli space, so define moduli space, we choose a set of parabolic weights, which is some real numbers, collection of the real numbers, and then write down the stability condition. So parabolic degree is defined in this way. And then we have like a stability depends on this choice. That is not that important in our. So once you have done this, and then we can define moduli space of the stable or semi-stable parabolic Higgs bundle, alpha stable or semi-stable Higgs bundles. But in this talk, in this work, I always assume that this alpha is genetic, which means that this implies in this, there's no strictly semi-stable object. So this is important. And then we also have a parabolic Hitchin map, which is nothing but just the usual Hitchin map, but forgetting about the flag. The flag data doesn't affect the definition of the parabolic Hitchin, because we just take the characteristic polynomial of the underlying meromorphic Higgs bundle. And same thing, like as I introduce the motivations, the structure that I want to look at is the global Poisson geometry. This is work of like Roberts and Marquez around 2010. And then more recently, Su and Wang studied like this integrable system structure. I'll come back to this point. But the point is that it's very similar to the meromorphic Higgs bundle. So I can ask the similar questions: what are the leaves? Or if you restrict the leaves, what are the bases, and how does it form a integrable system? Okay, so the candidate of a symplectic leaf is called C parabolic Higgs bundle. I know it's not a good notation, but I don't know what the better notation is. So this red, the text is in red. I choose another set of combinatorial data, which is just a collection of the complex numbers. The role of this CL to C1 to CL is that this second condition of this definition says that when you consider the residue, then it acts on the associated gradient. Yeah, so I can drop this. But it acts by the scalar multiplication of Xi. Which means that if you write down this residue in terms of matrix, so we have a block diagonal matrix, which block of size M1 to the ML. And then each diagonal block, they are just diagonal matrix. This is quite crucial. If they're diagonal matrix given by this eigenvalues. This is just an example. So probably the most familiar case is that when all these C's are all 0, then this is what is called the strongly parabolic Higgs bundles. And yeah, it was discussed in the Wang's talk yesterday, and also the previous talk. And the second example is that when R equals 2, I have two choices of this partition, because this is 2. Either this is 2 or this is 1, 1. So when equals 2, then I only have like one possible choice, C. And in order this matrix, or this what I write down is like a residue, it's C parabolic if and only if this diagonal, upper diagonal part is 0. For 1, 1, then it doesn't matter, because no matter what this star is, then this is always C parabolic for C1, C2. So this is the new object, which is smaller than the usual parabolic Higgs bundle, but it's kind of like analog of the strongly parabolic Higgs bundle. That's one way to think about it. Okay. So I denote the C par over here, the moduli space of this C parabolic Higgs bundle. And then the question is, like, what's the geometry of this parabolic Higgs bundle? And what happens when we restrict this to here? And how do I describe this base? And then how do I describe the fiber? There's more question about the global geometry. And so when Wang, I think, studied the Xi, when Xi equals all 0, which means the strongly parabolic Higgs bundle. And they know how to describe this base. So Wang explained this very well yesterday. So when C equals 0, this is shifted by what's called the level function. Okay, I'm not going to like combinatorial parts, but there are some shifts which capture the order of the spectral curve. So in the literature, it's well studied when m equals just full flag, which just means that all the m1 to ml is at ones. That's a full flag. Then this parameterizes this quotient, actually parameterizes a set of eigenvalues. But in general, this is no longer true. So that's why the problem of describing this base is quite difficult. So another remark is that, so this is, this is a full flag. Unless this is a full flag, we don't have this parabolic expander is not kind of foliated by this C parabolic expander. So definitely this is smaller. So I need to define kind of like a relative moduli problem, kind of collection of all possible C parabolic expander for by varying C. So I denote P. It's a relative moduli problem, which means that I considered all possible collection of this C. There's a residue condition, but I avoid saying that. But the generic fiber is what I just described, the moduli space of C parabolic expander, kind of like the big chunk of the usual parabolic expander. Okay, the first, any questions behind this?
So for general fact, so the unit is not equal to the whole space. Now, how much difference can you say? Where is it?
How much difference? For example, we don't have a Borel part. Yeah. For 2x2 matrices. Yeah. Well, let's say so m equals then we only know this kind of matrix, but we're missing this part. They live in the weakly parabolic expander. So yeah, sorry.
So can complement also be described as something more like some particular expanders?
Oh yeah, we can do that. We're varying, but okay, that's good question. So we can vary m. So if you want to describe this guy, then I can change a 1-1 instead of the 2. Yeah, but throughout this talk, try a fixed m. Okay, but you can also vary, and then it's kind of piled up. Yeah, there's good stratification. Thanks. Any other questions? Okay. So I described this relative moduli problem, and then first result is that this is smooth. Morphism is smooth, which means that in particular every C parabolic Higgs bundles are smooth, which is pretty nice. And then second result, some weird diagrams written there. I'm trying to explain. So it's what's called spectral correspondence. So I fix C. So it actually works over all it relatively works, but I've just fixed C. And on the left-hand side, I have the restriction of the parabolic Hitchin map. Right. On the right-hand side, there's something weird gadget here. And then my idea is that we actually closely embed this into some bigger moduli space, where this S, it's a bit of a lie here, but the holomorphic symplectic surface was obtained by some blowing up, iteratively blowing up the projectivization of this total complex, a total space, where the blow-up pattern determined by our combinatorial data. So once we have done that, we remove some infinity divisors and then vertical fiber. Then this is how we get. So once you have a surface, and you can consider the moduli of pure dimension 1 sheaves. I should have decorated all the topological type, but I only decorate the first trend class here, and then which is given by CM, which I don't give the proper definition, but I'll give you the examples. So it's too long to write down everything here. I'll try to give the examples of how this surface looks like and what's this curve class is. Then again, using the support map, then it lies into some affine subspace of the linear system. So what this diagram tells you that, like, once you know this embedding, then you can define the base of the Hitchin map, like, by just composing it. So this is a way to describe this appropriate Hitchin base when we have non-zero C values. One small remark is that this closed embedding is actually isomorphism when this C, all the values in C are distinct, and then it's a regular case. That's we have isomorphism. I'll come back to the point. Okay. So the analogy of this is that the usual VNR correspondence, but if you consider the Higgs bundle, moduli space of Higgs bundle, and one way to describe is that consider the total space of Kc, then pure dimension 1 sheaf with the appropriate curve class. And these two moduli spaces are isomorphic. That's another way to say the VNR correspondence. Done by Simpson, I mean. Okay. So what this result gives you, what's the definition of this BMC using this spectral correspondence? I'll give you quick examples. The first, I'm going to consider rank 2 and the partition 1, 1. And then this denotes the eigenvalue C1, C2. And if these two are different, in the surface, this is Kc, the total space of KCD. I have 2 points where like a P comma C1, P comma C2. What I do is just take the blow up this point. So we have like a P1, P1. It's called exceptional divisor. And I remove the strict transformation of this part. And then curve class that I want to look at is the pullback of this. So because it's rank 2, the spectral curve must be 2 to 1. But you like specify how it touches this point. Okay. So basically write down this is algebraically. But the funny thing, but this is already known. This is run by Donagi, like Pantev, Diaconus Donagi and Pantev, and then earlier work, some other people. But the interesting case is that same setup, but they are the same. Then slightly different, because you can think about this C1 and C2 actually kind of collide. If you think about the family, they can actually collide in one point. Then this exceptional divisor behaves like an iterative blow up. Then in this case, we have this term. Okay, this is a very basic examples of spectral correspondence. Sorry for not introducing all the generalized formal definitions. Once I've done this, I can say, okay, that we have like appropriate like a Hitchin base, which is affine space, and the dimension is actually the half of the dimension of the parabolic bundle. So we write down this HMC for the Hitchin map. Is the base is the smaller than the B. Now we have a right candidate. So what Ken is further saying is that this is a work in progress, but it's almost ready. It's probably put on the archive this month. And as I said, like this is a candidate of the symplectic leaf, and when this is also closed, because the condition of the parabolic is actually closed condition. So we have closed symplectic leaf, which means that this is smooth and satisfying this integrability condition, and also is connected. So for connectedness argument, I'll try to give you the proof, because what's difficulty playing with this non-zero C's? There's no C staction. So when C's are 0, you can think about because Hitchin base is actually affine subspace, vector subspaces. We can think of this C action. But there is no cis actions if we have like a non-zero cis. So that's one difficulty. But instead, we can think about a whole family, but this is actually cis equivariant. And furthermore, we can show using this Hitchin map, I can say that this is a semi-projective. Okay. So that means the relative moduli space is actually every fiber of this P is actually same cohomology, especially the H0. So since we know that the connectedness of this zero fiber, so it's also other fibers are also connected. Another result is that this forms actually the integrable system structure. We need to prove that the fiber is actually general fiber is abelian bright. So over the integral locus, so where the spectral curve is integral in the blown up surface and not the original surface, always not more non-integral. So with blown up surfaces, and if this is non-empty, then the spectral correspondence I wrote down is actually isomorphism. This is isomorphism over the integral locus. Okay. So this is how I get to show that the generic fiber is really infinite. Any questions?
So if your EMC still unstable.
Some effects. So this is a story on the parabolic Higgs bundles, and then one of the symplectic leaves is called the parabolic Higgs bundles. Then I'll get to the main point. So I need to relate this Higgs O, HHO, where O is adjoint orbit, with the parabolic Higgs bundle. So one way to do this is that given an adjoint orbit, we assign the combinatorial data such that the dual partition is collection of the size of the Jordan block, and C's are just eigenvalues. In other words, for example, if you start with this 2x2 matrix, which will be the orbits here, and if start as 1, this is a Jordan block of size 2, so M dual is 2, so M is 1, 1, and the is equals 1, 1. So if this is 0, then we have size 1, 1, then this becomes 2, which is dual, and then this is example. And what it means is that we can actually, okay. So also I denote like a O bar. HO bar is moduli space of Higgs bundle. The residue lies in the closure. So whole thing. So if O is like this star one, and the O bar is like everything. You allow this star to be 0. Okay. So we would like to describe the Hitchin base, but the way to describe the Hitchin base is that defined to be the one that we just described. Because if you pick a point, so any points in here, I can always find a compatible flag associated to this data. So for this, if you always like a star equals 1, then you have like a unique flag, but on the boundary, then you have a P1. This is usual like the resolution of important orbits by adding the flag. So I denote this O bar. I can denote by this associate MC depending on this choice of O. So, but the issue, it's not an issue, but it's quite difficult to understand like the Hitchin base for the HO, because this is locally closed. I don't know whether if we restrict this morphism to open locus, and whether the image is all or not. So we haven't figured out what that should be. So in the beginning of talk, I talked about restrict to this guy, we need to describe the Hitchin base BO, but I don't know the answer for that. But I also only know the answer for like a BO bar. Any questions? Just connections? So once we have like this correspondence between the orbits and the combinatorial data, what we can do is that to consider the forgetful map. Okay, so associate the data M, C, and O bar. I need to show that there's a forgetful map, but this forgetful map is between the moduli space, so I need to check some stability condition. Right? So stable objects goes to stable object instead. Then there's a little technical difficulties, like the technical things, but I need to choose like small enough probability weights. Then this is well defined between the moduli spaces. And then proposition we have is the forgetful map satisfying the following properties. First, it's surjective. So if you pick any element, you can always find the always parabolically lift. Also, this is projective. An interesting thing is that we have a like open locus. So it's on this like Higgs O, this is always 1-to-1. In fact, we can consider the symplectic forms and the symplectic forms here, and if you restrict to that, like this is actually the symplectomorphism. Also, by definition, this is also compatible with morphism. So we have like kind of like a Springer, like a resolution type for the moduli Higgs bundles for any adjoint orbits with closure. Any questions?
So each O bar has symplectic singularity.
Oh yeah. We need to show that it's O bar. Oh yeah, that's the result. Thanks. So the F gives the symplectic resolution is H O bar, and I need to show that like this is a symplectic leaf. Infinitesimal deformation part is actually easy, but not clear part is that how do we prove that like this is disconnected? Then if this morphism, but if this is smoothly connected and irreducible, so image is irreducible, it's surjective. So every open and irreducible is connected. So that's how we prove that this is actually global geometry, control the global geometry. And once you know that, it's not difficult to show that the closure is nothing but the closure inside the big moduli space of meromorphic. So also we need to also show that it is indeed singular. But yeah, the singularity comes from this singularity from O bar. So yeah, as you point out, this is like a symplectic, gives the symplectic resolutions. So one more thing, we always assume this R and D, right? But there's an interesting example where this is not the case. But if R and D is not coprime, then one needs to work with the semi-stable Higgs bundle. So I need to talk about the stability and semi-stability. So this map is actually semi-stable Higgs bundle, not just stable Higgs bundle. But in that case, we don't know whether this is surjective or not. So which means that every semi-stable meromorphic Higgs bundle in here, like there's a lift to the stable parabolic Higgs bundle. So it's a matter of the stability, not a matter of just the object. Anyway, in good case, if this is surjective, we can still say something. But one of the interesting example is that C the elliptic curve, and D equals, and we take O to be nilpotent orbit. We draw the normal form size of 2, 1, 1, 1, 1. Then mu of this is that R minus 1 and 1. So two block diagonal matrices. And then C equal to 0, 0 by the nilpotent orbits. So in this case, there's a well-known resolution of the singularity. So here is symmetric product of the cotangent space of the C. And this is corresponding to Higgs bar. And this is a C parabolic Higgs bundle with this combinatorial data. In that case, this is actually semi-stable. It's not stable. So in this case, we have a symplectic resolution. And then we have a two composition map, which is the obvious map. here. So this is the one key example of the whole story. You can, yeah, I stop it. Thank you.
Mentioned alpha is small enough
Yes.
symbolic weight. Right?
Yes.
So what does small enough?
Small enough means that I need to, so alpha is a real numbers, but less than 1. I need to make it smaller, like a very small epsilon.
So
Yeah.
why do you have such?
Because I need to show that every stable Higgs bundle actually should lift to the stable probably Higgs bundle and deal with the stability condition. So that's why where I need to play with this alphas. That's little technique.
So actually, I have one.
Yes.
So maybe a naive question. So do we expect some kind of for other groups, this HO bar still has symplectic singularity?
I guess so, but I don't know how to.
For example, in this case, you can have the parabolic nodal line, which is map weight,
Yes.
and you have the symplectic resolution. So for other cases,
Yeah, I think if you don't think about this Hitchin map and just a modularized spaces step, I believe I think you can do that. It's because like a matter of like the first we need to think about the infinitesimal deformation theory, show that the parabolic ones is smooth. That first step. But another step is that somehow prove the connectiveness. Otherwise, the argument, the statement should say that there is some resolution, but we need to take some connecting component. Yeah. But modulo that, I think that there should be.
oh, if no question, let's thanks to